Assalamualaikum warahmatullahi wabarakatuh and a very good morning. So welcome again to our lesson SEE 1223 Digital Electronics Chapter 6 Combinational MSI. So what we will learn today is we will learn about a Boolean function using multiplexer and also decoder. So at the end of this lesson, you will be expected to know how to design a multiplexer and decoder circuit based on the equation given by the questions. So without further ado, let's take a look. We start our lesson today by having some of the examples given in order for you to know how to design the circuit of multiplexer and also decoder. So these examples given a function of a, b and c equals to the minterm 1, 2, 4 and 5. Implement using the first question is 8 to 1 multiplexer. The second question is 4 to 1 multiplexer. The third question is 2 to 1 multiplexer. And the last question is 3 to 8 active low decoder. So, how to design it? Let's take a look at the next slide. Now, let's take a look at the first example of Boolean function using 8 to 1 multiplexer. So in this example, it shows that we have an expression of the minterm expression, which is interpreted as minterm 1, 2, 4, and 5. So basically, a minterm notations represent an output of 1 inside the truth table. So the first things that we need to do is we need to draw the truth table. So this is the truth table for this function, which is a function of a, b, and c. For the truth table, we have inputs and output, and we have all possibilities of the input. So this minterm notation represent a value of 1 at the row number 1, row number 2, row number 4, and row number 5 of the truth table. So the first row is actually row number 0. So as row number 0 is not being selected inside this expression, it will become 0. This is row number 1. So row number 1 is selected by this expression. So it will become 1. This is row number 2. It is also being selected. It will become 1. Row number 3, it is not being selected by this expression. So it will become 0. And row number 4, it is being selected. So it will become 1. And lastly, row number 5, it is being selected. And it will become 1. And the remaining rows of the truth table will become 0 because it is not being selected by this expression. Okay, so right now, how we wanted to interpret all the possibilities inside the truth table into 8 to 1 multiplexers. So before we proceed to the way of interpretations, we need to know what is the general representation of the multiplexer first. So this is actually the block diagram of the multiplexers, 8 to 1 multiplexers. So basically, multiplexers has a function as a data selectors in order to select the data based on the input which is being given to the selectors. So in 8 to 1 multiplexers, we have a total of 3 selectors, A, B, and C. And we have a total of 8 inputs which will be selected by the multiplexer, D0 until D7. And in this multiplexer example, we have an enable pin. So in this example, we have what we call active low enable because it has a bubble at the pin. And for the output, we have 2 types of output. So the first one is active high output, which is represented by Y, and also active low output, which is represented by WN because it has a bubble. Okay. So next, we need to know what is the output of each and every multiplexer by observing the input at the selectors. So for example, if A, we have input A, we have input B, and we have input C, which is corresponding to the function given. And in this situation, we have our output, which is y. So in this example, we are considering the active high output because it has not been considered in any of the question that it is mentioned that the output is active low. So we can generally consider the output to become active high. So for multiplexer, when A is equals to 0, B is equals to 0, and C is equals to 0, the output F will be equals to the first index of the input, which is D0. So F will be equals to D0. So when A is equals to 0, B is equals to 0, and C is equals to 1, the output of the multiplexer will become D1 because it selects the next index of the input. So next, if A is equals to 0, B is equals to 1, and C is equals to 0, what is the output of the multiplexer? Obviously, we can go to the next level of the input, which is D2. So F is equals to D2. And this, what they call this cycle, it goes on and on and on until it achieves 1, 1, 1, where A is equals to 1, B is equals to 1, and C is equals to 1. So in this situation, the output F will become D7. Okay. Now, how we want to interpret the function of the truth table so that it will be able to interpret this expression into 8-to-1 multiplexers. So basically, we can just observe at the output. So as I mentioned before, when A is equals to 0, B is equals to 0, and C is equals to 0, the output will select D0 as the output. So in order for us to what we call represent the output of 0 and 1, we need to use VCC and also the ground. So in this example, VCC represent the digital input 1 and the ground represent the digital output 0. So from the truth table, A is equals to 0, B is equals to 0, C is equals to 0, the output will become 0. So D0 is connected to the ground. So for the next example, 0, 0, 1. So the selectors will become 0, 0, 1. The multiplexer will choose D1 as the output. So D1 will become 1. So it will be connected to the VCC. Similar to the next one is 0, 1, 0, which is represent D2. So D2 will become 1. So D2 it is connected to VCC. Next is 0, 1, 1, which is represent D3. So the output here is 0. So D3 will be connected to the ground. And next, 1, 0, 0, which is represent D4. So 1, 0, 0 represent 1. So it needs to be connected to the VCC. Next is D5. D5 is represented by 1, 0, 1. So the output here is 1. So D5 will connected to the VCC. And for the remaining D6 and D7, it is the output will equals to 0. So it is directly connected to the ground. And please don't forget to connect your active low enable pin to the ground so that you will be able to activate the function of the multiplexer. So this is how you can design the 8-to-1 multiplexer circuit by interpreting this expression. Okay, you can observe at the output. So which output equals to 0 and which output will become 1. So the output which is equals to 0, you need to connect to the ground, and the output which is equals to 1, you need to connect to the VCC. In the previous example, you already seen that the expression of min term 1, 2, 4, 5 is already expressed in terms of 8 to 1 multiplexer. This next example shows how to interpret the same equations into 4 to 1 multiplexer. So the steps is just similar to the previous example, where the first step is you need to draw the truth table. So after you draw the truth table, you see here the output F is similar to the previous example. But this time, you need to insert the element of C inside the output equations, because the 4 to 1 multiplexer only have a total of 2 selectors. So it means that you need to have only 2 types of input that can be connected to the selectors. So in order for you to insert what they call the element of C inside the output, what you need to do is you need to compare the input C with the output F when the value of A and B is similar. So for the first example, when A and B is equals to 0, the C is equals to 0 and F is also equals to 0. And the second example, when A and B is equals to 0, the C is equals to 1 and F is equals to 1. So it means that F is equals to C in each and every situation when A and B is equals to 0. So the equation that we can get here is F equals to C. So next example shows the second level of A and B where A is equals to 0 and B is equals to 1. So we compare the value of C and F. So here you see that when C is equals to 0, F is equals to 1, and when F is equals to 0, C is equals to 1. So it means that F will be equal to the complement of C. So we can conclude that the equation of the output when A is equals to 0 and B is equals to 1 is F equals to C bar. So the third example is when A is equals to 1 and B is equals to 0. So the first state says C is equals to 0 and F is equals to 1. And when C is equals to 1, F is still equals to 1. So this statement says that it doesn't really matter what is the state of the C, the output will become 1. So the function of the output for A is equals to 1 and B is equals to 0 is F equals to 1. And lastly, when A and B is equals to 1, we compare the input C and output F. When input C is equals to 0, output F is equals to 0. When input C is equals to 1, output F is still equals to 0. So it means that it doesn't matter what is the state of C, the output is still become 0 when A and B is equals to 1. So it means that the output F is equals to 0. Now, let's take a look at the block diagram of the 4 to 1 multiplexer. In 4 to 1 multiplexer, we have a total of 4 inputs, 2 selectors, 1 active low enable input, 1 active high output, and we have 1 active low output. So, how to design the circuit of this expression into 4T1 multiplexer? Let's take a look at the next slide. So, you already know how the multiplexer works as the data selectors, where when A equals to 0 and B is equals to 0, the output Y will select D0 as the output. So in this situation, we already simplify the input number by moving C inside the output expression. So now we have 2 inputs, which is A and B. So those two inputs will be directly connected to the input A and the input B inside the selectors. And for the output F, it is connected to the active high output. So how to design the circuit of the input inside the 41 multiplexer? It is as usual, we need to have a VCC and also ground. And as you see here from the output equations, it has the variable C. So we need a variable C in this example. So in the first stage of the selectors, which is A equals to 0 and B is equals to 0, the output F is equals to C. So what we can do is we can directly connect C to the input D0. Next, we see that when A is equals to 0 and B is equals to 1, the multiplexer will choose D1 as the output. So you see here, the equation of the output is F equals to C bar. So what we can do here is we need to make the C to become C bar. So we need to put a NOT gate. So it will become C bar and it is connected to D1. Next is D2, which is when A is equals to 1 and B is equals to 0. So the output that we can get here is F is equals to 1. So in order for us to ensure that the D2 is equals to 1, we need to connect D2 to the VCC. And lastly, when A is equals to 1 and B is equals to 1, the output that we can get is F equals to 0. So in order for us to make the D3 is equal to 0, we need to connect D3 to the ground. And lastly, don't forget to connect your active low enable input to the ground so that your multiplexer will become functional. Okay, next example will show how to interpret this expression into 2 to 1 multiplexer. In this example, you will see how we can create a 2 to 1 multiplexer circuit by using the same expression that we have derived before. So as we are using the same expression, we will get the same truth table with the same output F. But this time, you need to reduce the number of input into only one input as the 2 to 1 multiplexer only contain one selector. So you need to merge input B and C inside expression output F. So in order to do that, first you need to divide it into two different sections where you need to get the expression where A is equals to 0 and A is equals to 1. So for the first expression when A is equals to 0, right now we are creating SOP expression. So we need to observe when the output is become 1. So the output is become 1 when B is equals to 0 and C is equals to 1. So from here, you can get an expression F equals to B bar C. And then you have another output when F equals to 1, when B is equals to 1, and C is equals to 0. So your expression is become B bar C plus B C bar. Okay. Next, when A is equals to 1, we observe the condition when F is equals to 1 to get the SOP expression. So the first expression that you can get is when F is equals to 1, you can get the first expression F equals to B bar C bar. And the second expression when F is equals to 1 is B bar C. And then this expression we can further simplify by factor out B bar and it will become B bar multiplied by C bar plus C, and C bar plus C, you can simplify it, and it will become B bar multiplied by 1, and finally, you can get the expression when A is equals to 1, F will become B bar. So, we already get the expression for each and every condition when A is equals to 0 and A is equals to 1. So, how to draw this expression into 2 to 1 multiplexers? So, before we proceed, we need to know what is the pin assignment for 2 to 1 multiplexers. So, for 2 to 1 multiplexer, we have 2 inputs, 1 selector, 1 active low enable, 1 active high output, and 1 active low output. So in order for us to connect the circuit of 2 to 1 multiplexer, you can just observe at the output equations. So the first one, we have input A that will be directly connected to the selectors. And we have output F, which will be directly connected to the output active high Y. And then, in order for us to draw the 2 to 1 multiplexer circuit, you need to know how this circuit works. When A is equals to 0, Y will select D0 as the output. So here, when A is equals to 0, the output will become B bar C plus B C bar. So we need a variable B and also C inside this circuit. So as you can observe from this expression, actually this expression represents the XOR operation, where B bar C plus B C bar can be directly connected to the XOR gate. So B and C connected to the XOR gate, and it will become B bar C plus B C bar. And then you see here, when A is equals to 1, Y will be choosing D1 as the output. So when A is equals to 1, the output F will become B bar. So in order for us to convert B into B bar, you can just simply connect B to the NOT gate for it to become B bar, and then connect to the D1. And finally, don't forget to connect your active low enable input to the ground so that your multiplexer will be operated. Let's take a look at the example of designing the same expression by using the 3 to 8 decoder. But before we proceed with the design process, let's take a look at the pin assignment of the 3 to 8 decoder. So in this example, we are using a 74138 IC for the 3 to 8 decoder. So in this IC, we have a total of 3 inputs, which is A, B, and C. We have 1 active high enable input. We have 2 active low enable input. And we have 8 total of active low output. So, by using this IC, how to design the decoder circuit? Let's take a look at the next slide. The procedure of implementing the 3 to 8 decoder circuit for this expression is similar to the previous example, where the first procedure is to create the truth table. So as we already shows how to create the truth table in the previous example, we already get the output of the expression. So for the 3 to 8 decoder, the function of the decoder is to detect the specific pattern of the input, and it will be indicated by the output activation. For example, when input A is equals to 0, B is equals to 0, and C is equals to 0, the output Y0N will be activated by giving 0 to the output. So as you can see from our function, we have a total of 3 inputs, and our decoder also have 3 inputs. We can directly connect our input with the decoder input. To activate the decoder, you need to give an input to the active high and active low enable pin. So for active high enable pin, you need to give the VCC input. And for active low enable pin, you need to give the ground input so that your decoder will be functional. Okay, as you can see here, the output of the decoder has a total of 8 output, but your expression only allows one type of output only, okay? One bit of output. So in order for you to get one bit of output, you need to merge each and every output inside the decoder by using a logic gate. So you see here, in order for you to create a Boolean function, you need to observe the output where it is equals to 1. Okay, you see here 001 equals to 1, 010 equals to 1, 100 equals to 1, and 101 is equals to 1. So in order for you to generate the output of 1 when this condition is being fulfilled, you need to connect of each and every activation function that has the output of 1. For example, at 000, y0n will be activated. At 001, y1n will be activated. At 010, y2n will be activated, and so on. So for this expression, at 001, y1n, 010, y2n, 100, y4n, and 101, y5n. So all of the aforementioned connection need to be connected to OR gate. But before it is connected to OR gate, you need to connect it to the bubble first, because it is active low decoder. So because of the active low output decoder, we need to cancel out the active low activation function in order for us to get the output of 1 inside the F. So for the first example, let's say A is equals to 0, B is equals to 0, and C is equals to 0. So when this situation is fulfilled, y0n will be activated, and it will become 0 because it is active low output. And the other pin will become 1. So as the connected pin to the OR gate will be connected to the bubble, so each and every pin which is equals to 1 will become 0. And after we execute the OR operation, which is the OR gate, the output F will become 0. So it fulfills the condition of A equals to 0, B equals to 0, C is equals to 0. The output will become 0. So next example, when A is equals to 0, B is equals to 0, and C is equals to 1. So for this type of expression, y1n will be activated, and it will become 0, and the other output pin will become 1. So as it travels throughout the bubble, it will become 1, and the other pin will become 0 because it is initially 0. And after we execute the OR operation, the output will become 1. So it fulfills the condition of when A is equals to 0, B is equals to 0, C is equals to 1, the output will become 1. And let's take a look at the final example. When A is equals to 0, B is equals to 1, C is equals to 0, y2n will be activated, and it will become 0. And the other pin will become 1. So, as usual, when it goes through the bubble, the output will become complement each other, and it will become 0, 1, 0, 0. And after we execute the OR operation, the output will become 1. And it is also fulfill the condition of 0, 1, 0. So, from this example, you can see that in order for you to design the circuit of 3 to 8 decoder of the Boolean expression, you need to connect the output to the OR gate. But you need to remember, only the output that gives the 1 output signals need to be connected to the OR gate. And you need to observe what type of output, either it is active low or active high. You need to ensure that the availability or the requirement of bubble is needed or not, in order for you to get the correct output. So at the end of this lesson, you need to do 2 assessments. And the assessment, given Boolean expression A C bar plus A bar B bar C bar plus A bar B bar C bar plus A bar multiplied by B XOR operation C, you must implement using 8 to 1 multiplexer, 4 to 1 multiplexer, 2 to 1 multiplexer, and also 3 to 8 active low decoder. And for second assessment, given Boolean expression the function of x, y, z, the max term MO, M1, M2, and M4, implement using 4 to 1 multiplexer, 2 to 1 multiplexer, 3 to 8 active low decoder, and 2 to 4 active low decoder. So all of this assessment you need to submit inside your e-learning portal, and it will be calculated for your assessment throughout your marks in your subject. So that's all for today. Thank you.